Right now, all around you sits space that looks completely empty. Yet inside that empty space, trillions of tiny explosions happen every single second. Particles blink into existence and vanish before you can even blink your own eyes. Scientists call this the quantum vacuum, and it might be the strangest place in the entire universe. Today we travel into fields that fill every inch of space, a force that pulls metal plates together with nothing between them, and a mismatch between prediction and reality so enormous that some call it the worst calculation ever made in science. If your mind is ready to have its idea of empty broken apart, hit like and subscribe before we start. Take a breath. Empty space is about to get very crowded. Picture a glass box with all the air pumped out. No dust, no gas, no light. Scientists call this a vacuum, and for centuries people believed a perfect vacuum held absolutely nothing. That belief is dead. Long before quantum physics entered the picture, a German scientist named Otto von Guericke performed a public demonstration that stunned an entire audience. He joined two large copper hemispheres, pumped the air out between them, then hitched teams of horses to each side. The horses could not pull the two halves apart, held together purely by the pressure of an ordinary vacuum. Physicists now know every corner of the universe, even inside that sealed glass box, stays busy at a scale too small to see. Space behaves like the main performer in its own story, always moving, never pausing for a break. Here is the twist that changes everything. What looks empty to your eyes is packed with invisible fields, stretching across every inch of the universe, humming with activity all the time. Your body sits inside these fields right now. So does this room, this street, this entire planet. Scientists measure this activity with extremely sensitive equipment, and every single test agrees. The vacuum of space carries real energy, energy that pushes on matter, bends light, and even makes tiny objects move without anyone touching them. Think about a calm ocean on a still day. From a distance, the water looks flat and lifeless. Zoom in close enough though, and you find billions of tiny ripples, far too small to see from shore, constantly rising and falling. Empty space works the same way. Calm on the surface, wild underneath. This idea comes from quantum mechanics, the branch of physics that studies the smallest building blocks of reality. Quantum mechanics has a strange rule. Nothing in the universe is ever allowed to sit perfectly still, and nothing is ever allowed to be perfectly empty. That single rule breaks apart everything humans used to believe about nothingness. For most of history, thinkers pictured a vacuum as the ultimate silence, the absence of everything. Isaac Newton assumed space could be truly empty. Ancient philosophers argued for centuries about whether true nothing could even exist. Then, in the 20th century, quantum physics stepped in and settled the argument in the strangest way possible. The math showed that a region with zero particles, zero light, and zero matter still carries energy. The numbers involved can grow almost too large to believe, numbers we will get to later in this journey. Right now, hold on to the basic shock. Nothing, in the way you have always imagined it, does not exist anywhere in this universe. Every patch of space you can point to, from the inside of a light bulb to the gap between Earth and the Moon, roughly 240,000 miles away, buzzes with these hidden fields. Scientists have confirmed pieces of this picture through real experiments, ones we will walk through step by step. Other pieces remain deeply mysterious, pieces that keep top researchers up at night. One thing is certain: the moment you stop thinking of empty space as nothing and start thinking of it as a living, breathing ocean of fields, the universe becomes a far stranger place than you ever imagined. That ocean has a name, and it is about to rewrite everything you thought you knew about the word empty. For a long time, people pictured the universe as built from tiny solid balls like microscopic marbles bouncing around in the empty space. Atoms, then electrons, then quarks, each one imagined as a small hard dot. That picture is outdated. Modern physics describes the universe using something far stranger: fields. A field is an invisible presence that fills all of space, like an ocean without any edges. Every type of particle you have ever heard of comes from its own field, stretching everywhere, filling this room, filling the space between galaxies, filling everything. Physicists now describe an electron as a small disturbance in the electron field, similar to a wave rising up from the surface of the ocean, replacing the old picture of a solid little ball floating through empty space. Light works the same way, rising from the electromagnetic field. Even the particles that make up your body come from their own hidden fields that existed billions of years before you did. Here is a comparison that makes this easier to picture. Imagine a still pond covered in a thin sheet of ice. Tap the ice and a small ripple spreads outward. That ripple is not a separate object dropped onto the ice. The ripple forms from the ice itself, a temporary shape rising from something that was already there. Particles work the same way. They are temporary ripples rising from fields that never go away. This means the universe stays completely full, wall to wall, with overlapping fields, rather than mostly empty space with a few particles scattered around inside it. Particles are simply the moments when those fields get excited enough to show themselves. Physicists reached this conclusion through decades of experiments, tested again and again in particle accelerators around the world. Machines like the Large Hadron Collider, buried underground near the border of France and Switzerland, smash particles together at incredible speeds, specifically to study how these fields behave. Every result lines up. Fields are real. Fields are everywhere. Particles are simply the visible tip of something much larger, always hidden just beneath the surface. The standard model of particle physics, the most rigorously tested theory science has ever produced, describes about 17 separate fields, each one responsible for a different family of particles, from quarks and electrons to the Higgs field that gives many particles their mass. Add every field together, and you account for essentially all matter and all forces in the observable universe, aside from gravity itself, which still resists a full quantum description. This idea forces a huge shift in how you should picture the universe. Stars, planets, oceans, your own hands right now, all of it floats inside fields that never switch off, never take a break, never leave a single cubic inch untouched. Even stranger, these fields do not stay calm. They twitch, they jitter, they produce brief flickers of activity even in regions with absolutely no matter present at all. Those flickers are where our story turns dangerous for old ideas about nothingness, because a field that twitches on its own, with nothing pushing it, breaks a rule that once felt unbreakable. Something in the deepest layer of reality refuses to sit still, and the reason traces back to one of the strangest laws in all of science, a law about to make true emptiness completely impossible. A rifle can aim at a precise target with confidence, knowing both the bullet's speed and its exact path. That kind of certainty runs into a wall the instant physicists shrink down to the size of an electron. In 1927, physicist Werner Heisenberg discovered a rule that reshaped science forever. He found that a particle's exact position and its exact speed can never both be known at the same time. Pin down one, and the other blurs into fuzzy uncertainty. This became known as the uncertainty principle, and it stands as one of the most tested, most confirmed ideas in all of physics. Heisenberg first worked out this idea while collaborating with physicist Niels Bohr in Copenhagen, wrestling with strange results coming out of early atomic experiments. Measuring an electron's exact location, they realized, always disturbed its speed, and no clever new instrument could ever fix that problem, since the fuzziness lived inside nature itself, not inside any measuring device. At first, this sounds like a limit on human measurement, like a blurry camera lens that just needs a better focus. It runs far deeper than that. The uncertainty principle describes a genuine fuzziness built into reality itself. That same fuzziness applies to energy and time. A tiny patch of space cannot hold exactly zero energy for any length of time, because that would mean knowing both the energy and the timing with perfect precision, something the universe refuses to allow. Picture trying to balance a coin perfectly on its edge, then freezing time completely so the coin can never tip over. The coin will always find a way to wobble. Empty space works the same way. It cannot sit in a state of exact frozen nothingness, so it wobbles instead. This wobble comes with a price. A patch of space must constantly borrow small amounts of energy, use it briefly, and pay it back before anyone notices, since it cannot hold zero energy for good. These tiny loans happen trillions of times each second in every cubic inch of the universe, including the empty air around you right now. Scientists have measured the effects of these energy loans in laboratories, confirming this strange borrowing really happens. We will step inside one of those experiments soon. For now, picture what this means for the idea of nothingness. A true vacuum, one with zero particles and zero energy, forever frozen and unchanging, cannot exist anywhere in this universe. The uncertainty principle forbids it. Space stays required by the deepest laws of physics to remain a little bit restless. This restlessness has a name: quantum fluctuation. Each fluctuation appears and disappears almost instantly, faster than any camera could ever capture. Yet these fluctuations leave real fingerprints scattered across the universe. Some fluctuations may have kicked off the entire universe in the earliest sliver of time after the Big Bang, stretched by cosmic expansion into the seeds that eventually grew into galaxies. Other fluctuations happen inside your own body this very second, though at a scale far too small for any of your cells to notice. The uncertainty principle turns empty space into something closer to a pot of water that never quite stops simmering, even with the stove switched off. Something in that pot is about to boil over into full view, taking the shape of particles that seem to break the deepest rules of physics, yet somehow exist anyway, if only for the briefest possible moment. Somewhere in the empty space above your head, right now, a pair of particles just flickered into existence. They did not come from a star. They did not come from a lightning bolt or a nuclear reactor. They came from nothing, borrowed briefly from the restless fields we just uncovered, and they vanished again before you finished reading this sentence. Physicists call these virtual particles, and they appear in matched pairs, one particle and its opposite twin, called an antiparticle. An electron might pop into being alongside a positron, its antimatter partner. A pair like this exists for a length of time so short that human language barely has a word for it, often less than a trillionth of a second. Then, just as quickly, the pair collides and destroys itself, cancelling out completely, repaying the tiny energy loan the uncertainty principle allowed it to take. No flash of light follows, no leftover heat remains, only the fields settle back down until the next flicker happens somewhere else. Here is a comparison that captures the pace of this event. Imagine striking a match in complete darkness, seeing a flash for a single instant, and having the match disappear before your eyes even register the brightness. Virtual particles blink in and out, even faster than that, over and over, everywhere, all the time. Trillions of these flickers happen every second inside a space no larger than a grain of sand. Multiply that across the size of a football field, a city, an entire planet, and the total number becomes almost impossible to picture. Scientists sometimes describe the vacuum as a boiling froth, and the comparison earns its place. This same flickering happens far from Earth too, in the cold vacuum stretching between stars, across the vast gap separating our sun from its nearest neighbour, roughly 25 trillion miles away. Every cubic inch along that entire distance stays caught in this constant flickering. Physicists sometimes compare the effect to static on an old television screen, tiny, random, and utterly relentless. Except this static fills the entire universe rather than one glowing screen, and no antenna could ever tune it away. For decades, some physicists wondered whether this idea sounded too strange to be real, more like a mathematical trick than an actual physical event. Real experiments eventually erased that doubt. Devices sensitive enough to detect the fingerprints of these fleeting particles have confirmed that this boiling process genuinely happens in the real, physical universe. What makes this discovery so unsettling is the scale. These events happen constantly, everywhere, filling every inch of the universe with a storm of particles too fast and too small for the human eye, or even the most advanced microscope, to catch directly. Your living room right now hosts this storm. So does the space between your fingertip and this screen. So does the entire volume of the observable universe, stretching billions of light years in every direction. These virtual particles seem to break an old and sacred law of physics, one that says energy can never simply appear from nowhere. The universe found a clever loophole around that law, a loophole so strange that it forces scientists to rethink what the words exist and real even mean. Real particles play by strict rules. A real electron carries a fixed mass, a fixed charge, and a predictable amount of energy, values that never change no matter where in the universe you find it. Virtual particles ignore those rules completely. A virtual particle can carry energy that does not match its supposed mass, something a real particle could never get away with. Physicists describe virtual particles as existing off-shell, a term borrowed from geometry, meaning their properties fall outside the normal boundaries that real, lasting particles must obey. Think of it like a student sneaking into a test using a fake identification card. The card works well enough to get through the door for a few brief moments, but it would never survive a closer inspection. Virtual particles slip through the universe's rulebook the exact same way, using a kind of borrowed identity that only holds up because the moment passes too quickly for anyone, or anything, to check. This shortcut exists because of the uncertainty principle explored earlier. Since energy and time can never both be pinned down with total precision, a particle can briefly violate the normal energy rules, as long as it pays back that violation fast enough that no measurement could ever catch it in the act. Here comes the detail that keeps physicists awake at night. Even though virtual particles never survive long enough to be directly observed, they still leave measurable effects behind. They nudge other particles. They alter the strength of forces at extremely small distances. They shift the exact colours of light given off by atoms, shifts so small and so precise that only specialised laboratory equipment can detect them. One of these effects, called the Lamb shift, was measured back in 1947 and matched theoretical predictions about virtual particles so closely that scientists could no longer treat this idea as pure speculation. The prediction and the measurement lined up almost perfectly, a level of agreement rare enough in science to feel almost eerie. This shows up in an even more dramatic way inside the hydrogen atom itself. Virtual particles constantly surround the single electron orbiting a hydrogen nucleus, nudging it just slightly with every flicker. That nudge shifts the electron's energy by an almost impossibly tiny amount, yet physicists can measure that shift using precision spectroscopy, comparing the exact colour of light the atom gives off against theoretical predictions calculated down to a dozen decimal places. The two numbers agree with a precision unmatched almost anywhere else in science. Proof that these invisible, fleeting particles leave a permanent signature on the ordinary matter around us. This tells us something remarkable. Virtual particles never show up directly on any detector, since they exist for far too short a time. Their fingerprints still show up everywhere, scattered across dozens of separate experiments, all of them agreeing with the same underlying mathematics. Picture invisible ghosts, ones who can never be photographed directly, yet who leave objects rearranged and lights flickering every single time they pass through a room. Scientists only catch the evidence these ghosts leave behind, since the ghosts themselves always slip away too fast to see. This ghostly evidence builds towards something even stranger, a place where these fleeting flickers stop being invisible background noise and start pushing on real, physical objects with enough force to measure directly, using nothing more exotic than two ordinary metal plates. A puddle sits still on a sidewalk. Drop a single pebble into it, and a ring of ripples spreads outward, rising and falling before settling back into stillness. That ripple never existed as a separate object. It rose directly out of the water itself, a temporary shape made from something that was already there. Every electron in the universe, including the ones racing through the wires in your walls and the ones spinning inside every atom of your body, behaves exactly like that ripple. Physicists describe the electron field as an invisible presence that fills every point in space, stretching across the entire universe without a single gap. When this field gets excited at one particular spot, with just the right amount of energy, a ripple rises up. That ripple is what we call an electron. The electron field stays fixed everywhere, at every location, forever, unlike the water in a puddle, which drains away and moves from place to place. Only the ripples move, rising, travelling, sometimes settling back down. This explains one of the strangest facts in all of physics. Every single electron in the universe carries the exact same mass, the exact same charge, down to the tiniest measurable decimal. 2 electrons, one sitting inside a rock on Mars and one sitting inside your own eye right now, are perfectly identical in every measurable way. That kind of perfect matching would be a wild coincidence if electrons were tiny separate objects, manufactured one at a time somewhere in the universe. It makes complete sense once you realize every electron comes from ripples in the exact same underlying field, like waves rising from one single, unified ocean rather than countless separate ponds. This same logic applies to antimatter as well. A positron, the antimatter twin of an electron, rises from a completely separate field running parallel to the electron field, mirroring it in almost every way except for a flipped electric charge. Whenever the 2 fields interact just right, an electron and a positron can meet, cancel each other out, and release a burst of pure light, converting the ripple of one field directly into a ripple of the electromagnetic field instead. This idea extends beyond electrons. Photons, the particles that make up light, rise from the electromagnetic field. Quarks, the tiny building blocks packed inside every proton and neutron, rise from their own quark fields. Each type of particle traces back to one field, stretched across the whole universe, humming quietly everywhere at once. Here is where things turn strange again. These fields never fully calm down, not even in regions with 0 particles present. The restless energy from the uncertainty principle keeps every field jittering constantly, producing those brief virtual ripples explored earlier, flickers that rise and fall too fast to count as full, real particles. Sometimes, given the right conditions, these tiny jitters can grow strong enough to leave a lasting mark on the world, strong enough to bend beams of light, pull objects toward each other, or even leak particles away from the crushing gravity of a black hole. One of the clearest proofs of this hidden ocean of fields does not come from deep space at all. It comes from a tabletop experiment using 2 ordinary pieces of metal, placed extremely close together, with nothing visible pushing them at all. Cool any object down enough, and its atoms slow to a crawl. Cool it down to negative 459 degrees Fahrenheit, a temperature scientists call absolute zero, and classical physics predicted every last bit of motion should stop completely. That prediction turned out to be wrong. Even at absolute zero, the coldest temperature theoretically possible in the entire universe, atoms and fields refuse to sit perfectly still. A small amount of motion remains locked in place, permanently, called 0-point energy. This leftover jitter comes directly from the uncertainty principle, the same rule that makes true nothingness impossible. Picture a child on a swing at a playground, pushed just once, then left alone forever. Normal physics says friction and air resistance should eventually bring that swing to a complete stop. 0-point energy says a small ghostly motion remains in the swing no matter how long you wait, a tiny leftover wobble that quantum rules refuse to erase. 0-point energy shows up in real, measurable ways across chemistry and physics, far more significant than a small footnote buried inside a textbook. It explains why helium, cooled down close to absolute zero, refuses to freeze into a solid under normal pressure, since its atoms still carry enough leftover jitter to keep sliding past each other like a liquid. 0-point energy also plays a role inside the Sun. Deep in the Sun's core, hydrogen atoms slam together to create helium, releasing the energy that eventually reaches Earth as sunlight and warmth. 0-point motion gives those hydrogen atoms an extra, permanent nudge, helping them overcome forces that would otherwise keep them apart, making nuclear fusion easier to achieve than classical physics alone would predict. Scientists have measured 0-point energy directly in careful laboratory experiments, involving tiny mechanical devices cooled down to nearly absolute zero. Even after removing every scrap of heat technology allows, a small residual vibration always remains, exactly matching the predictions of quantum theory. Engineers building the world's most precise atomic clocks run directly into this leftover motion. Even inside a single trapped atom, cooled and isolated as carefully as modern technology allows, 0-point energy causes a tiny, unavoidable wobble that limits exactly how precise these clocks can ever become. Scientists must account for this wobble in their calculations, treating it as a permanent feature of nature rather than a flaw waiting to be engineered away. Here comes the detail that connects everything back to our main mystery. Zero-point energy exists inside every single quantum field stretched across the universe, including fields in regions with zero particles present at all. This means empty space itself carries a permanent baseline hum of energy, one that can never be fully removed, no matter how much cooling or emptying you attempt. Add up this tiny hum across every field at every point in space, throughout the entire universe, and the numbers involved grow so large that they eventually create one of the biggest headaches in modern physics, a mismatch we will confront directly in a few chapters. For now, picture the coldest, emptiest region conceivable, a spot with no light, no matter, no heat, cooled as close to absolute zero as physics allows. Even there, something keeps humming, a hum about to become powerful enough to pull two solid objects together, using nothing you could ever see, hear, or touch directly. Take two flat metal plates, polished smooth, and place them close together in a vacuum chamber with nothing between them. No air, no wires, no magnets. Classical physics predicts the plates should stay perfectly still, floating with no force acting on them at all. They move anyway, sliding slowly toward each other, pulled by a force invisible to every instrument except the ones designed specifically to detect it. In 1948, Dutch physicist Hendrik Casimir predicted this strange pull using the mathematics of quantum fields. His idea sounded almost too bizarre to test at the time. Decades later, improved technology finally allowed scientists to check his prediction directly, and the plates moved exactly the way his equation said they would. Here is the explanation behind this strange pull. Remember those restless quantum fields filling every corner of space, constantly flickering with virtual particles? Between two metal plates, only certain wave patterns fit neatly, similar to how only specific musical notes fit perfectly inside the length of a guitar string. Outside the plates, in the open space around them, every possible wave pattern gets to exist freely. This creates an imbalance. Slightly less quantum activity happens in the tight gap between the plates compared to the open space surrounding them. That imbalance creates a tiny pressure difference, and pressure differences push objects around. The open space on the outside effectively pushes the plates together, since less pressure exists on the inside to push back. Picture two people standing in a narrow hallway, crowded with a moving, jostling crowd on either side. If fewer people can squeeze into the hallway itself compared to the open lobby areas outside it, the crowd outside will end up shoving the two people closer together, purely through the difference in crowding. The strength of this pull changes dramatically depending on the distance separating the two plates. Halve the gap between them, and the force jumps by a factor of 16, growing far faster than most everyday forces people experience. This sharp scaling explains why the Casimir effect stays completely unnoticeable in daily life, yet becomes powerful enough to dominate the behavior of machinery once engineers shrink components down to distances measured in millionths of an inch. The Casimir effect measured in laboratories matches this prediction with remarkable precision, especially when the plates sit extremely close together, often less than the width of a human hair apart. At that tiny distance, the pull becomes strong enough for sensitive equipment to detect directly, confirming the reality of this quantum vacuum pressure with numbers that match theory almost perfectly. This experiment carries enormous weight for our entire investigation. It proves that the vacuum, the supposedly empty space between those two plates, carries real, physical energy capable of pushing on solid matter. This stands as a real, measurable, repeatable force, confirmed again and again across labs around the world. Engineers have even begun exploring whether this strange force might someday help build incredibly small machines, ones so tiny that ordinary friction and gravity barely matter. Machines where this ghostly vacuum pressure could become the dominant force at play. If two motionless metal plates can feel a genuine tug from empty space, one question becomes impossible to avoid. What else might this invisible ocean of energy be capable of, especially in regions of the universe far more extreme than a quiet laboratory table? Physicist Steve Lamoureux spent the mid-1990s building an experiment so delicate that a single stray vibration from a passing truck outside the building could ruin months of careful work. His goal was to measure the Casimir effect directly, with enough precision to compare the results against Hendrik Casimir's decades-old prediction. In 1997, Lamoureux published his results. The force he measured matched the predicted value within a small margin of error, confirming that empty space really does push on solid matter with a measurable strength. Picture trying to weigh a single snowflake using a bathroom scale meant for a grown adult. That gives you a sense of just how faint this force actually is, and how much skill it took to detect it cleanly, separate from every other force competing for attention in the same tiny space. A year later, physicists Umar Mohideen and Anushree Roy repeated the experiment using an atomic force microscope, a tool normally used to study surfaces at the scale of individual atoms. Their results matched the prediction even more closely than before, tightening the agreement between theory and reality even further. Later experiments pushed the precision even further. In the early 2000s, researchers refined the measurement using improved plate coatings and better vibration isolation, narrowing the gap between theory and observation to within a fraction of 1%. Each improvement chipped away at any lingering doubt, turning what began as an exotic theoretical curiosity into one of the most thoroughly confirmed predictions inside all of modern physics. These experiments confirmed far more than one clever prediction from 1948. They confirmed an entire framework of quantum field theory, the same framework responsible for everything explored in this journey so far, from virtual particles to zero-point energy to the restless jitter locked inside every corner of space. Since those early breakthroughs, the Casimir effect has been measured using dozens of different setups: spheres near flat plates, tiny gold-coated beams, even microscopic machines built onto computer chips. Each new method reduces the noise a little further, and every single result keeps agreeing with the same underlying theory. Engineers eventually started worrying about this force for a very practical reason. As computer chips shrank smaller and smaller, packing components closer together, tiny moving parts inside these chips began sticking together unexpectedly. Investigators traced the problem back to the Casimir effect, an invisible vacuum force strong enough, at these microscopic distances, to jam machinery that should have moved freely. This turned an abstract quantum mystery into a genuine engineering headache, one that chip designers now account for directly when building extremely small mechanical devices. A force born from the emptiness of space had grown powerful enough to interfere with human technology. Every one of these confirmations chips away at the old idea that a vacuum holds nothing at all. Real laboratories, using real equipment, keep proving that empty space carries real energy, energy capable of nudging metal, jamming machines, and shaping the tiniest structures humans have ever built. If empty space can push solid objects together here on Earth, using forces this small and this precise, an unsettling question starts to form. What happens when this same restless energy interacts with something far larger and far stranger, something capable of bending light itself? A powerful magnetic field strong enough to rip metal tools out of a technician's hands from across a room sits at the center of a strange experiment happening in laboratories today. Physicists aim a laser through this magnetic field, then check whether the light comes out changed in any way. According to old-fashioned physics, empty space should never affect a beam of light passing through it. Light should travel in a perfectly straight line, completely unaffected by anything, since nothing physically present exists to interact with it. Quantum field theory disagrees, and it makes a bold prediction. An extremely powerful magnetic field, combined with the restless virtual particles hiding inside empty space, should very slightly bend and twist a passing beam of light. Scientists call this vacuum bifringence, and hunting for it has become one of the most ambitious experiments running today. Here is the mechanism behind this strange prediction. Remember those virtual particle pairs flickering constantly throughout empty space, popping into existence for a fraction of an instant before disappearing again. A strong enough magnetic field can nudge these virtual particles just slightly before they vanish, and that tiny nudge changes how light passing through the same region behaves. Picture throwing a ball through a curtain made of countless invisible, extremely fast-moving threads. Under normal circumstances, the ball passes straight through without any resistance. Stretch those threads tight enough, and the ball starts to curve slightly as it passes, deflected by threads too fast and too thin to see directly. This effect remains so small that even our most advanced lasers and magnets have not yet detected it with full certainty. Researchers working with facilities capable of generating incredibly powerful magnetic fields have reported early hints matching the prediction, though the scientific community still waits for a result strong enough to remove all doubt. Facilities chasing this signal include specialized laboratories in Italy and Germany, where physicists fire lasers through some of the strongest sustained magnetic fields ever produced on Earth, generated using powerful superconducting magnets originally designed for other branches of physics entirely. Detecting the predicted twist requires isolating an effect thousands of times smaller than the best equipment can currently distinguish from ordinary background noise. This search matters enormously, because catching this effect directly would offer some of the most powerful proof yet that empty space genuinely bends light, using nothing but its own hidden quantum activity. It would mean the vacuum actively participates, shaping and steering light in ways that classical physics never predicted, rather than serving as a passive stage where light simply travels through. A similar effect may already be happening around one of the most extreme objects known to exist anywhere in the universe: the incredibly strong magnetic fields surrounding neutron stars, collapsed stellar remnants so dense that a single teaspoon of their material would weigh billions of tons. Some astronomers believe light bending near these objects already shows faint signs of this same vacuum effect, hinting that nature may have already run this experiment for us out among the stars. If empty space can twist light using magnetic fields, this extreme, one location in the universe pushes these effects into an entirely different category of strange, a place where gravity grows so intense that light cannot escape at all, and where the vacuum starts producing something even stranger than a bent beam. A black hole earns its name honestly. Gravity near its center grows so extreme that nothing, not even light traveling at 186,000 miles per second, can escape once it crosses a boundary called the event horizon. For decades, physicists assumed black holes were perfect prisons, swallowing everything nearby and giving nothing back. In 1974, physicist Stephen Hawking overturned that assumption, using the same quantum field ideas explored throughout this journey. Hawking realized that virtual particle pairs, the same fleeting flickers born from restless quantum fields, appear near a black hole's edge, just as they appear everywhere else in the universe. Normally these pairs collide and cancel out within an instant, leaving no trace behind. Near a black hole, something different can happen. Occasionally, one particle from the pair falls across the event horizon, while its twin escapes outward into space. The particle that falls in never gets the chance to collide with its partner and cancel out. The particle that escapes becomes real, permanent, and detectable, carrying energy away from the black hole in the process. Picture two skydivers jumping from a plane, tied together by an invisible cord, meant to reunite the instant they land. Now imagine one skydiver getting swept away by a powerful gust of wind mid-fall, pulled permanently off course, while the other lands safely and simply walks away. The cord that should have brought them back together snaps, and only one skydiver survives the jump as a lasting presence. This escaping particle became known as Hawking radiation, and it represents one of the most celebrated predictions in modern physics, even though scientists have not yet directly detected it from a real black hole. The radiation predicted from most known black holes stays far too faint, buried underneath the much louder background radiation filling the rest of the universe. The temperature of this radiation depends entirely on a black hole's size, and the relationship runs backward from what most people expect. A colossal black hole millions of times heavier than our Sun radiates at a temperature colder than the emptiest depths of interstellar space. A tiny black hole, by contrast, would radiate ferociously hot, blazing with escaping particles right up until the final moment it disappeared completely. Despite this, scientists have found strong indirect support for Hawking's idea. Researchers built artificial sonic black holes in laboratories using flowing fluids that trap sound waves instead of light, creating a controllable stand-in for a real black hole's extreme gravity. In 2019, physicist Jeff Steinhauer and his team detected radiation from one of these sonic black holes that closely matched Hawking's original prediction, offering some of the strongest evidence yet that this strange process really happens. Hawking's discovery connects two of the most extreme ideas in all of physics: quantum fields and the crushing gravity of collapsed stars. A black hole, once considered the ultimate one-way trap in the universe, turns out to leak, slowly and steadily, thanks to the same restless quantum jitter buzzing through empty space everywhere else. That leak carries a consequence far stranger than anyone expected at first. Every time this radiation escapes, the black hole itself pays a price that eventually adds up to something almost impossible to imagine: the total disappearance of an object once thought to be eternal and unstoppable. Every particle pair born near a black hole's edge starts out completely balanced, one particle and one antiparticle, carrying matched but opposite properties, exactly like the virtual pairs flickering everywhere else in the universe. The event horizon changes everything about how that balance plays out. Cross that invisible boundary, and gravity grows so overwhelming that escape becomes physically impossible, even for light itself. A particle trapped on the wrong side of that line stays trapped permanently, with no way back. This creates an extremely one-sided outcome for the pair. If both particles happen to end up outside the event horizon, they usually collide and cancel out almost instantly, just like normal virtual particles everywhere else. If both particles happen to fall inside the event horizon together, they get swallowed as a matched cancelled pair, leaving the black hole basically unaffected. The interesting case happens when the pair splits directly across that boundary line, one particle just inside, one particle just outside, at the exact moment they separate. The trapped particle falls deeper into the black hole, gone forever. The particle on the outside keeps travelling outward, escaping into open space as genuine detectable radiation. Picture a tug-of-war rope stretched directly across a rapidly moving river. One person on the near bank suddenly stumbles, gets swept downstream by the current, and disappears from view. The person on the far bank, still holding tight to the rope, gets yanked forward by the sudden shift, sent stumbling away from the riverbank entirely. Here comes the part that keeps this idea firmly grounded in real physics. The particle that falls inward carries what physicists describe as negative energy relative to an outside observer, a strange quantum bookkeeping trick made possible by the extreme gravity near the event horizon. That negative energy effectively subtracts from the black hole's own mass the instant it falls inside. Meanwhile, the particle that escapes carries positive energy outward into the universe, detectable in principle by any telescope pointed in the right direction, at the right time, with sensitive enough equipment. Physicists sometimes describe this negative energy trick using an accounting analogy that makes the strange math easier to accept. Imagine a shared bank account where withdrawing money from one branch instantly adds that same amount to a different branch across town. The black hole acts like the branch losing money every time a trapped particle carries negative energy inward, while the escaping particle represents the matching deposit showing up somewhere else out in open space. No money vanishes from the system as a whole. It simply moves from one place to another exactly the way total energy across the universe always has to balance in the end. This process happens gradually, particle pair by particle pair, an incredibly slow trickle compared to the enormous size of most black holes. A black hole the mass of our own sun would take a length of time vastly longer than the current age of the universe to fully evaporate through this process alone. Smaller black holes lose mass much faster than larger ones, since the effect grows stronger as an object shrinks. This detail sets up one of the strangest predictions to come out of this entire discovery, one that turns black holes from permanent monsters of the cosmos into objects with a genuine ticking expiration date. Every black hole in the universe, from the smallest ones formed by a collapsing star to the supermassive giants sitting at the centre of entire galaxies, currently loses mass through Hawking radiation, drop by drop every single second. This trickle happens so slowly for large black holes that the effect stays completely undetectable, using any equipment humans have ever built. A black hole with the mass of our sun radiates so little energy through this process that its own temperature sits far colder than the leftover glow from the Big Bang, which currently bathes the entire universe at roughly negative 455 degrees Fahrenheit. This creates a strange problem. A large black hole actually absorbs more energy from that leftover cosmic glow than it loses through Hawking radiation, meaning most black holes in today's universe are technically still growing rather than shrinking, at least for now. That balance will not last forever, As the universe continues expanding, the leftover glow from the Big Bang keeps cooling further and further, eventually dropping below the radiation temperature of even the largest black holes. Once that crossover point arrives, expected in a length of time so enormous that current numbers struggle to express it meaningfully, every black hole in the universe will begin losing mass faster than it gains it. Picture an ice cube sitting inside a freezer, staying frozen and stable as long as the freezer stays cold enough. Slowly warm that freezer over an impossibly long stretch of time, and eventually the ice cube starts melting, faster and faster as it shrinks until nothing remains. Black holes follow a similar pattern once they start losing more mass than they gain. As a black hole shrinks, Hawking radiation grows stronger, which causes the black hole to shrink even faster, creating a runaway process that accelerates toward the very end. Physicists predict this final stage unfolds in a dramatic burst, sometimes called the black hole's death, releasing a final flash of energy before the black hole disappears completely, converting its remaining mass entirely into escaping radiation. For a black hole with the mass of our own Sun, current calculations suggest this entire process, from formation to final evaporation, would take longer than the current age of the universe, multiplied by trillions upon trillions of times, making direct observation impossible for any process we could ever hope to witness. Smaller black holes could theoretically evaporate on far shorter timescales, and some scientists once wondered whether powerful machines like the Large Hadron Collider might briefly create tiny black holes that would evaporate almost instantly through this exact process. No such particles have shown up in over a decade of searching. Astronomers have never observed a real black hole reach this final stage either, since even the smallest black holes discovered so far, formed from collapsing stars, still carry far too much mass to finish evaporating within any timescale humans could ever witness or record. What began as two metal plates pulled together by empty space has now grown into a force capable of erasing the most powerful objects in the entire universe. This same restless vacuum energy carries one more secret, buried inside a single number so far off from reality that some physicists consider it the most embarrassing calculation in the history of science. Every quantum field explored throughout this journey carries its own zero-point energy, that permanent, unavoidable hum locked into empty space itself. Physicists eventually attempted a bold calculation: add up the total zero-point energy from every known field across all of space and figure out exactly how much energy a vacuum should contain. The math produced a number. Then, astronomers compared that number against real measurements taken from deep space, checking how much energy actually appears to fill the universe based on how galaxies move and how the cosmos expands. The two numbers did not match. They failed to match by a margin so enormous that scientists needed a completely new way to describe just how wrong the prediction turned out to be. The calculated value came out somewhere between 60 and 120 powers of 10, larger than what astronomers actually observe in the real universe. Picture trying to guess the weight of a single grain of sand and having your estimate come back heavier than every ocean, every mountain, and every planet in the solar system combined. That comparison barely scratches the surface of how far off this particular calculation landed. Physicists sometimes call this mismatch the vacuum catastrophe, or the cosmological constant problem, named after a term Albert Einstein originally introduced into his equations for an entirely different reason back in 1917. Einstein later called his own use of the term his biggest blunder, never suspecting that decades later it would return at the centre of one of physics' deepest unsolved mysteries. Each individual piece of the calculation follows directly from quantum field theory, the same framework responsible for virtual particles, the Casimir effect, and Hawking radiation, all of them confirmed repeatedly through careful laboratory experiments. That success makes the mismatch even harder to explain away. A framework that gets so many other predictions exactly right somehow produces a wildly incorrect answer the moment scientists apply it to the total energy of empty space itself. Physicists have tried narrowing the calculation by only counting zero-point energy up to a certain smallest possible distance, called the Planck length, rather than assuming fields stretch down to infinitely small scales. Even this adjustment, meant to tame the runaway math, still produces a number roughly 120 powers of 10 too large, showing just how stubborn this particular mismatch remains, no matter which reasonable assumption gets applied to the calculation. Some researchers now suspect the true answer will only arrive alongside a full theory of quantum gravity, a framework capable of describing both the smallest particles and the curved fabric of space-time itself, using one unified set of equations, a goal physicists have chased for nearly a century without success. Researchers have proposed dozens of possible explanations over the decades. Some suggest a missing piece of physics that cancels out most of this energy through some mechanism scientists have not yet discovered. Others suggest new particles or forces waiting to be found, ones capable of balancing out this enormous mismatch. None of these explanations have been confirmed. The vacuum catastrophe remains one of the largest open questions in all of modern science, a genuine mystery sitting at the intersection of quantum physics and the study of the entire universe. Before diving deeper into possible explanations, the size of this mismatch deserves a closer, more careful look, set directly against the real number astronomers actually measure coming from deep space itself. Astronomers have a genuinely reliable way to measure how much energy fills empty space across the universe. They study how fast galaxies move away from each other, tracking the expansion of the universe itself using powerful telescopes and decades of careful observation. These measurements consistently point to a specific value for the energy density of empty space, a small but real number that helps explain why the universe keeps expanding the way it does. Scientists have confirmed this number repeatedly, using different telescopes, different methods, and different research teams scattered across the globe, all arriving at results that agree closely with each other. The measurements astronomers rely on come from several independent methods that all happen to agree with each other. Observations of exploding stars called supernovae, patterns frozen into the leftover glow from the Big Bang, and the way galaxies cluster together across the cosmos all point toward the same small value for the energy of empty space. That kind of agreement across completely different techniques gives scientists strong confidence in the observed number, which makes the enormous gap against theoretical prediction even harder to dismiss as some kind of simple measurement error. Quantum field theory, working from a completely different direction, predicts its own value for this same energy density calculated by adding up the 0-point energy from every known particle field in existence. Set these two numbers side by side, and the difference becomes almost impossible to comprehend. The theoretical prediction lands somewhere between 1 followed by 60 zeros and 1 followed by 120 zeros times larger than the number astronomers actually observe out in the real universe. Picture the distance across the entire United States, roughly 3,000 miles from coast to coast. Now picture trying to measure that distance using a ruler, except your ruler predicts the country stretches far wider than the entire visible universe. That comparison still falls short of capturing the true scale of this mismatch, since numbers this large stop making intuitive sense to the human mind entirely. Scientists sometimes describe this gap using a simpler comparison instead. Imagine a bank account prediction that says a person should have exactly $120 trillion, and checking their real balance reveals just one single dollar sitting inside. The theory and reality point toward wildly different outcomes, even though both started from the exact same basic math. This mismatch forces an uncomfortable conclusion. Either quantum field theory contains some deep, currently unknown flaw, specifically related to how it handles empty space, or some other unknown mechanism, force or particle, actively cancels out almost the entire predicted energy, leaving behind only the tiny sliver astronomers actually detect. Researchers have spent decades searching for that missing mechanism, testing dozens of proposed solutions against real astronomical data. So far, none of these proposals have fully solved the mismatch in a way the broader scientific community fully accepts. This puzzle sits at the center of modern cosmology, connecting the smallest possible scale, individual quantum fields, to the largest possible scale, the expansion of the entire visible universe. Solving it could reshape our understanding of gravity, quantum physics, and the ultimate fate of everything that exists. Some physicists have given this mismatch an even blunter nickname, one that captures just how strange it feels for one of science's most successful frameworks to produce a number this far removed from reality. Physicist and Nobel laureate Steven Weinberg once described the mismatch between predicted and observed vacuum energy as the worst theoretical prediction in the entire history of physics. Other researchers have echoed similar language over the decades, calling it an embarrassment, a scandal, or simply the biggest unsolved puzzle connecting quantum physics to the study of the cosmos. This reputation makes sense once you consider how successful quantum field theory has been everywhere else. The same mathematical framework predicts the strength of the force holding atoms together with an accuracy matching experiments down to 11 decimal places, among the most precise agreements between theory and measurement in the entire history of science. That same framework, applied to the total energy of empty space, produces an answer wrong by dozens of powers of 10. Few other areas of physics show this dramatic a split between spectacular success and complete failure, all coming from the exact same underlying equations. Some researchers suspect the problem traces back to how physicists calculate zero-point energy in the first place, treating each quantum field as if it stretches on forever, uninterrupted, down to impossibly tiny distances. Others believe a still undiscovered symmetry in nature might cancel out most of this energy automatically, a mechanism physicists have not yet identified despite decades of searching. One especially popular idea, called supersymmetry, proposed that every known particle has an as-yet undiscovered partner particle, and that these partners would naturally cancel out much of the runaway vacuum energy through the mathematics of the theory. Powerful experiments at the Large Hadron Collider searched directly for evidence of these partner particles for over a decade. None have turned up so far, and many physicists now consider the simplest versions of supersymmetry increasingly unlikely, forcing researchers back toward the drawing board in search of a different explanation. A newer idea, called the anthropic explanation, takes a completely different angle. It suggests that many different regions of the universe, or perhaps entirely separate universes, could exist with wildly different vacuum energy values. Only regions with a vacuum energy close to the tiny number we actually observe would allow galaxies, stars, and eventually life to form at all. Under this view, we measure a small number, simply because a much larger one would have prevented anyone from existing to measure anything in the first place. This explanation remains deeply controversial, since testing it directly would require access to other universes entirely, something no telescope or experiment has any current way to achieve. A newer proposal called the swampland conjecture approaches the problem from string theory, suggesting that only a narrow range of possible vacuum energy values can ever exist within any mathematically consistent universe. If true, this idea would rule out many of the countless imagined universes physicists once considered possible, tightening the puzzle considerably rather than solving it outright. Researchers continue testing this proposal against astronomical data, hoping it might eventually connect the impossibly small number we observe to some deeper, still hidden structure inside the laws of physics themselves. Whatever the true answer turns out to be, this mismatch connects directly to something astronomers discovered completely independently, through a totally different line of research. The surprising, ongoing acceleration of the universe's expansion, a discovery that reshaped our entire understanding of the cosmos, and one that traces suspiciously close to this same restless vacuum energy hiding inside empty space. In 1998, two separate teams of astronomers set out to measure how quickly the expansion of the universe was slowing down, fully expecting gravity to be gradually pulling every galaxy back toward every other galaxy, the same way gravity always behaves. Both teams found the opposite result. The expansion of the universe was speeding up, not slowing down, and it had been speeding up for billions of years already. This discovery shocked the scientific community so deeply that researchers spent months double-checking their instruments, their calculations, and their assumptions, certain they must have made some kind of mistake somewhere along the way. The result held up under every check, and the teams eventually shared a Nobel Prize in 2011 for uncovering one of the strangest facts ever discovered about the universe. Scientists needed a name for whatever force was pushing galaxies apart at an accelerating pace, so they called it dark energy. Nobody fully understands what dark energy actually is, even today, though its effects show up clearly and consistently across dozens of independent astronomical measurements. Here comes the connection that ties this entire journey together. The simplest explanation for dark energy treats it as the energy of empty space itself, the exact same vacuum energy explored throughout every chapter of this story, from virtual particles to zero-point energy to the crushing mismatch uncovered in the vacuum catastrophe. Under this view, empty space carries a small but genuinely real amount of energy, spread evenly throughout the entire universe. As the universe expands and creates more space, it simultaneously creates more of this vacuum energy along with it, since the amount of energy per region stays constant even as the total volume grows larger. Picture a rubber sheet stretched wider and wider, with tiny dots printed evenly across its surface representing this vacuum energy. Stretch the sheet, and the total number of dots grows along with it, since the space between existing dots fills up with new ones as the material spreads out. This growing reservoir of vacuum energy would explain why the universe's expansion keeps accelerating rather than slowing down, and it matches beautifully with everything explored throughout this entire journey, from Casimir plates pulled together by nothing to particles born and destroyed near the edge of black holes. The catch brings us straight back to the vacuum catastrophe. The amount of dark energy astronomers actually measure sits nowhere close to the enormous value predicted by adding up zero-point energy across every known quantum field. The same mismatch explored earlier returns here, in a completely different context, connecting the smallest possible scale in physics to the largest possible scale in the entire cosmos. Space telescopes launched specifically to study dark energy, including missions designed to map the positions of billions of distant galaxies, continue gathering data aimed at pinning down exactly how this mysterious push has behaved across billions of years of cosmic history, searching for any subtle change that might finally reveal what dark energy truly is. Empty space, once dismissed as nothing worth studying at all, now sits at the center of two of the biggest open questions in modern science: why galaxies keep rushing apart at an ever-increasing speed, and why the universe's own energy refuses to add up the way our best equations insist it should. Drop a ball into the air, and gravity pulls it back down, slowing its climb with every passing second. For most of the universe's history, scientists expected a similar story on the cosmic scale. Every galaxy pulls on every other galaxy, and that pull should have dragged the expansion of the universe into an ever slower crawl. Real measurements from deep space tell a different story completely. The universe passed through an early chapter dominated by radiation, then shifted into a long era dominated by ordinary and dark matter, both of which thin out as space stretches, weakening their gravitational grip on the cosmos over time. Vacuum energy behaves in a completely different way. As space expands, the amount of matter squeezed into any given region keeps shrinking, since the same particles now spread across a larger volume. Vacuum energy stays locked at a constant density everywhere, no matter how much space stretches, since it belongs to space itself rather than to any object floating inside it. Picture a crowded party inside a room that keeps growing bigger. The people at the party spread out thinner and thinner as the room expands, just like matter thinning out across an expanding universe. Vacuum energy behaves like wallpaper covering every wall of that room. However large the room grows, the wallpaper still covers every inch of it, at exactly the same thickness. Billions of years ago, matter dominated this cosmic tug-of-war, and its pull was strong enough to slow the expansion down. As matter thinned out across billions of years of cosmic growth, vacuum energy's steady, unchanging push eventually overtook it, and the balance flipped. Roughly 5 billion years ago, astronomers calculate the universe crossed that tipping point, and expansion started accelerating instead of slowing. Astronomers first uncovered this timeline by studying a special class of exploding stars called Type Ia supernovae, stellar explosions so consistent in brightness that scientists use them as reliable cosmic yardsticks, sometimes nicknamed standard candles. By comparing how bright these explosions should appear against how bright they actually appear from Earth, researchers can calculate precisely how far away each explosion happened, and precisely how fast the universe was expanding at that particular moment in cosmic history. That acceleration has only strengthened since, and current models predict it will keep strengthening for the rest of cosmic history. Distant galaxies, already rushing away from us, will eventually cross a boundary where their light can never reach Earth again, vanishing from view permanently one by one over unimaginable stretches of time. Future astronomers living far enough ahead in cosmic time may look up at a night sky containing only their own galaxy and its closest neighbours, every other galaxy having drifted forever beyond view, an isolation almost impossible to picture from where we stand today. This raises an unsettling question that goes beyond simple bookkeeping between matter and vacuum energy. Gravity should only ever pull things together, an attractive force everywhere it appears throughout the universe. Vacuum energy somehow reverses that rule entirely, pushing space apart rather than pulling it together, and explaining that reversal requires digging into one of the strangest ideas hidden inside Einstein's own equations, an idea most people never expect gravity to be capable of at all. Ordinary gas trapped inside a sealed container pushes outward against the container's walls, exerting what physicists call positive pressure. Vacuum energy carries a property that sounds almost like a contradiction. Negative pressure, a kind of pressure that pulls inward on any imaginary boundary, rather than pushing outward against it. This detail might sound like a small technical footnote, except it sits at the very centre of why the universe accelerates. Einstein's theory of general relativity describes gravity as a response to both energy and pressure combined, not simply a response to how much mass or energy sits inside a region. Under normal circumstances, positive pressure adds to the pull of gravity, making objects attract each other slightly more strongly than mass alone would suggest. Negative pressure flips that contribution completely, and vacuum energy carries negative pressure strong enough to overwhelm its own gravitational pull, turning what should attract into something that repels instead. Picture stretching a rubber band between two hands. The rubber band naturally wants to pull your hands together, resisting the stretch with tension. Vacuum energy behaves like a rubber band running in reverse, a strange tension that pushes your hands apart the wider you stretch it, growing stronger rather than weaker as the distance increases. Einstein actually predicted this exact possibility back in 1917, adding a term to his equations called the cosmological constant, specifically to allow space itself to carry this kind of repulsive push. At the time, astronomers believed the universe stayed perfectly still, neither expanding nor shrinking, and Einstein used this term to balance gravity's pull and keep his model frozen in place. Once astronomers discovered the universe was expanding rather than sitting still, Einstein dropped the term, later regretting he had ever introduced it. Decades later, the discovery of accelerating expansion brought this exact same idea roaring back, except now pointing in the opposite direction entirely, explaining a universe that speeds up rather than one that stays frozen. Physicists sometimes describe this relationship using something called the equation of state, a simple ratio comparing an object's pressure to its energy density. Ordinary matter carries a ratio close to zero, exerting almost no meaningful pressure at cosmic scales. Vacuum energy carries a ratio close to -1, meaning its pressure sits almost exactly equal in size to its energy density, just pointed in the opposite direction. That specific ratio turns out to be exactly what a repulsive push requires. Measuring this ratio precisely has become one of the major goals driving modern cosmology, since even a slight deviation from -1 could reveal that dark energy changes its behavior gradually over cosmic time, rather than staying perfectly constant. Several space telescopes and ground-based surveys currently track this number, using distant supernovae and the large-scale clustering of galaxies, hunting for any subtle drift that might hint at deeper physics still waiting to be discovered. This means the emptiest regions of the universe, the vast stretches of space between galaxy clusters, containing almost no matter at all, actively push against everything around them. Every cubic mile of seemingly empty space between here and the nearest galaxy carries this same repulsive push, working relentlessly and invisibly across the entire cosmos. That repulsive push traces back to fields whose behavior grows even stranger the deeper physicists probe, all the way down to a scale where the very fabric of space and time itself starts to unravel into something almost impossible to picture clearly. Zoom into any smooth surface far enough, and eventually the smoothness breaks down. A polished tabletop that looks perfectly flat reveals jagged mountains and valleys, once viewed under a powerful microscope, made from individual atoms stacked unevenly against each other. Physicist John Wheeler proposed in the 1950s that space and time themselves might follow this same pattern, staying smooth and predictable at every scale humans can directly observe, while turning violent and chaotic at a scale far smaller than any atom, smaller than any particle ever detected inside the most powerful colliders on Earth. Wheeler called this idea quantum foam. At this extreme scale, the fabric of space itself stops behaving like a smooth flat stage and instead churns and bubbles, warping and twisting from one instant to the next, driven by the same restless quantum uncertainty explored throughout this entire journey. Picture the choppy, foamy surface of ocean waves crashing against rocks during a violent storm, full of unpredictable peaks, tiny whirlpools and bubbles popping in and out of existence within a fraction of a second. Quantum foam behaves the same way, except the crashing waves are made from space and time themselves rather than water. At this scale, some physicists speculate that space might briefly develop tiny wormholes, microscopic tunnels connecting one point to another, popping into existence and collapsing again almost instantly, far too quickly and far too small for any experiment to catch directly. Others suggest tiny bubbles resembling miniature black holes might flicker in and out of existence constantly, part of the same restless churning. None of these predictions have been directly confirmed through experiment, since the scale involved sits so far beyond what any instrument built by humans can currently reach. The idea remains grounded in solid mathematics rather than pure speculation, emerging naturally from combining quantum mechanics with Einstein's theory of gravity, two frameworks that work beautifully on their own, yet clash dramatically the moment scientists try to unite them at this extreme scale. This clash represents one of the biggest unsolved problems in all of physics, a missing theory of quantum gravity that could finally explain what really happens to space and time at their most fundamental foamy level. The most powerful particle collider ever built, the Large Hadron Collider, can only reach a tiny fraction of the energy required to probe this scale directly, falling short by a factor larger than 1 trillion multiplied by another trillion. Reaching energies high enough to observe quantum foam directly would likely require a particle accelerator the size of an entire galaxy, a machine that will almost certainly remain forever out of reach for human engineering. Some physicists have proposed indirect methods instead, hunting for extremely subtle side effects of this foam on light that has travelled across billions of light years from distant explosions called gamma-ray bursts. If quantum foam genuinely roughens the path light takes through space, the tiniest blurring or delay might show up after a signal has crossed a large enough stretch of the universe, offering a possible indirect window into a scale direct experiments cannot reach. That missing theory has a target scale with a very specific name, and reaching it would mean shrinking down past every atom, every proton, and every distance ever measured by any scientific instrument in existence. Every ruler, no matter how finely marked, eventually reaches a limit where measuring anything smaller becomes physically impossible, not because of a lack of clever engineering, but because reality itself refuses to allow it. Physicists call this ultimate limit the Planck length, named after physicist Max Planck, one of the founders of quantum mechanics. This distance sits almost unimaginably smaller than anything discussed so far in this journey, smaller than an atom by a margin. Larger than an atom is smaller than the entire visible universe. Here is why this limit exists. Measuring an extremely tiny distance requires an extremely powerful burst of energy, concentrated into an extremely small space, similar to how a sharper pencil point requires pressing harder against the paper to make a smaller mark. Push that energy concentration far enough, and something strange happens. The energy becomes dense enough to collapse into a black hole. Once that collapse happens, the black hole swallows the very measurement being attempted, along with any information about the distance scientists were trying to measure in the first place. The Planck length marks the exact point where this collapse becomes unavoidable, the smallest distance that could ever be measured even in principle, using any conceivable future technology. Picture trying to read the fine print on a page using a magnifying glass so powerful that the concentrated sunlight passing through it burns straight through the page, before your eyes can ever focus on the words. Below the Planck length, the very act of looking destroys the thing you're trying to see. Space itself keeps existing below this scale, even though our ordinary ideas about distance, position and geometry, the same ideas that work perfectly for describing everything from atoms to galaxies, stop making reliable sense once you shrink down this far. To put this scale into perspective, imagine shrinking the entire visible universe down until it fits inside a single grain of sand. Even after that almost unimaginable shrinking, an ordinary atom inside that shrunken universe would still measure vastly larger than the Planck length compared to everything around it. No everyday comparison captures this ratio comfortably, since human intuition never evolved to handle a gap this extreme. This tiny scale also sets a natural boundary for the energies involved. Reaching a Planck length would require an amount of energy packed into a single particle, far beyond anything the most powerful cosmic accelerators, including the explosive centers of active galaxies, have ever been observed producing. That energy requirement helps explain why quantum foam and the deepest layer of space-time remain firmly outside the reach of direct experimental testing, even using the most extreme natural laboratories the universe has to offer. Physicists strongly suspect something entirely different takes over at that scale. Some deeper structure underlying space and time that our current theories cannot yet describe. Whatever that structure turns out to be, it likely holds the key to finally explaining the quantum foam explored a moment ago, along with the still unsolved mismatch behind the vacuum catastrophe uncovered earlier in this journey. Reaching that deeper structure remains one of the greatest unfinished projects in the history of science, and the leading guesses about what lies beneath grow stranger with every attempt to picture them clearly. Scientists cannot directly observe anything smaller than the Planck length, yet that has not stopped physicists from building serious mathematical theories about what might be happening down there, underneath the smooth surface of space and time as we experience it. One leading idea, called loop quantum gravity, proposes that space itself comes in tiny discrete chunks, similar to how a photograph made of individual pixels only looks smooth and continuous from a normal viewing distance. Zoom in far enough on that photograph, and the illusion of smoothness breaks apart into countless separate squares. Loop quantum gravity suggests space works the same way, built from tiny individual units too small for any of our senses to detect directly. A completely different idea, called string theory, proposes that the smallest building blocks of reality are not points at all, but incredibly tiny vibrating loops, far smaller than any particle ever detected. Under this view, different vibration patterns in these loops produce all the different particles found throughout the universe, similar to how different vibration patterns on a guitar string produce different musical notes. A third approach, called causal dynamical triangulations, builds up the shape of the universe from countless tiny triangular building blocks, similar to how a curved dome can be built from flat triangular panels bolted together. Run the mathematics forward, and something remarkable happens. A smooth, four-dimensional universe naturally emerges from these tiny discrete pieces, without anyone needing to assume smoothness from the start. Each of these theories makes a bold, competing claim about the deepest layer of reality, yet none has been confirmed through direct experimental evidence, since testing any of them would require energies and precision far beyond anything current technology can achieve. Each of these competing frameworks makes different predictions about details that might, one day, become testable indirectly. Loop quantum gravity predicts subtle effects on how light of different energies travels across cosmic distances, potentially arriving at slightly different times after crossing billions of light years. String theory predicts the existence of extraspatial dimensions, curled up so tightly that they remain completely undetectable, at any scale humans currently have the ability to probe. Some physicists remain hopeful that gravitational wave detectors, instruments sensitive enough to catch ripples in spacetime caused by colliding black holes, might eventually pick up faint signatures of this deeper quantum structure, assuming those signatures turn out to be strong enough to survive the long journey across the universe. Some physicists have proposed an entirely different possibility, called the holographic principle, suggesting that everything happening inside a three-dimensional region of space might actually be fully described by information stored on a flat two-dimensional surface surrounding it, similar to how a hologram printed on a flat card can display a full three-dimensional image when light passes through it correctly. If true, this would mean the three-dimensional world you experience every day, filled with depth and distance, might be a kind of projection, built from information encoded on some deeper, flatter surface most of us will never directly perceive. None of these ideas have won the argument yet, and the true answer may combine pieces of several theories at once, or turn out to be something no physicist has imagined so far, a genuine mystery still waiting for its solution. Turn on a radio anywhere in a city, and it can pick up dozens of different stations, each one broadcasting its own separate signal, all travelling through the exact same air, at the exact same time, without ever colliding or interfering with each other in any way you could notice. Quantum fields behave the same way, layered on top of each other throughout every inch of space. The electron field, the electromagnetic field, several separate quark fields, the Higgs field, and dozens of other fields described by the standard model of particle physics, all occupy the exact same space at the exact same moment, stacked on top of each other like invisible sheets of glass. Each field carries its own separate rules, its own separate jitter, and its own separate contribution to the restless quantum activity buzzing throughout empty space. These fields never physically crowd each other out the way solid objects would, since fields are not made of matter competing for room. They behave more like separate layers of possibility, each one ready to produce its own type of particle the instant enough energy gets concentrated in the right spot. Physicists organize these fields into broader categories based on how they behave. Matter fields, including the electron field and the various quark fields, follow one set of mathematical rules. Force-carrying fields, including the electromagnetic field responsible for light and the separate fields responsible for the strong and weak nuclear forces holding atomic nuclei together, follow a different set of rules entirely. Even neutrinos, ghostly particles that pass through entire planets without interacting even once, trace back to their own dedicated field, humming quietly through you at this very moment, completely unnoticed. Trillions of neutrinos pass through your body every single second, produced mostly by nuclear reactions happening inside the Sun, and almost none of them ever interact with a single atom inside you during your entire lifetime. Right now, sitting in the chair beneath you, standing in the room around you, and stretching through the empty air above your head, every single one of these fields exists simultaneously, filling the exact same volume of space you currently occupy. Your own body, in fact, exists because ripples in several of these fields happen to be locked together in a very specific organized pattern. Picture an orchestra where every single instrument plays constantly, all at once, forever, layered together into one continuous, invisible performance, filling the entire concert hall from wall to wall. Most of the time, this performance stays so quiet and so subtle that nobody in the audience notices anything happening at all. Every so often, a single instrument grows loud enough to stand out clearly, producing something we recognize directly, a particle, a force, a flash of detectable energy. Scientists have spent nearly a century mapping out exactly how many of these fields exist and how they interact with each other, confirming their predictions through thousands of separate experiments conducted at particle accelerators scattered across the globe. This layered structure raises an important question about scale and location. If every cubic inch of space carries this same crowded stack of invisible fields, does anywhere in the entire universe ever manage to escape them completely, even in the darkest, coldest, most isolated corners imaginable? Deep between galaxy clusters, astronomers have mapped out regions of space so empty of matter that they earned a chilling nickname: cosmic voids. The largest known void stretches across roughly 1 billion light-years, a region so vast and so thin on matter that entire galaxies inside it sit separated by distances almost impossible to picture. Even inside these cosmic voids, the quantum fields explored throughout this journey remain fully present, humming with the exact same restless activity found anywhere else in the universe. Matter can thin out until only a scattered handful of atoms remains inside an area the size of an entire solar system. The underlying fields never thin out at all, since they belong to space itself rather than to the matter floating inside it. Some of these voids stretch so wide that light itself, the fastest thing in the universe, would need hundreds of millions of years just to cross from one edge to the other. Standing at the center of one, a hypothetical observer would see almost no galaxies at all in any direction, an isolation more extreme than anything experienced anywhere on Earth. Yet even at the exact geometric center of the emptiest known void in the entire universe, every quantum field described throughout this journey remains completely present, flickering with virtual particles and carrying its full share of zero-point energy, exactly as thoroughly as the space inside your own living room. This distinction matters enormously. Removing every particle from a region of space removes the matter, yet the fields always remain, since those fields make up the very fabric that space is built from in the first place. Asking whether a region of the universe could exist without its underlying quantum fields is a bit like asking whether an ocean could exist without any water, a question that stops making sense the moment you examine it closely. Picture the coldest, emptiest desert imaginable, stretching in every direction with no plants, no animals, and no water in sight. Even in a desert this empty, the air itself still fills every space between the grains of sand, invisible yet completely present everywhere you could possibly stand. Quantum fields fill the universe with that same total, inescapable completeness, minus even the air, since fields exist in the vacuum of space just as thoroughly as anywhere else. Astronauts travelling through the emptiest stretches of the solar system, far from any planet or star, still travel through this same invisible ocean of fields, exactly as thoroughly as someone standing on the surface of Earth. No spacecraft has ever travelled far enough, and no distance has ever proven great enough to reach a region genuinely free of this underlying structure. This raises a much stranger possibility than simple emptiness. If the vacuum surrounding us represents just one possible state these fields could settle into, a question worth asking is whether this particular state counts as the most stable one available, or whether a deeper, more stable state might exist somewhere else entirely waiting to be reached. That question carries consequences far more serious than pure curiosity, consequences that touch on whether the vacuum we live inside might not be as safe and permanent as it first appears. Picture a hiker standing inside a shallow mountain valley, surrounded by gentle slopes on every side. From where the hiker stands, this valley looks like the lowest point around, a comfortable, stable place to set up camp for the night. Farther in the distance, hidden behind a ridge, sits a much deeper canyon, dropping down to a floor far lower than the valley the hiker currently occupies. Physicists use almost exactly this picture to describe two different possible states of the vacuum. A state resting in a shallow dip, stable enough to last a very long time but not sitting at the true lowest possible energy, gets called a false vacuum. A state resting in the deepest possible dip, the true lowest energy configuration available anywhere in the underlying fields, gets called the true vacuum. Current measurements of particle physics, especially measurements involving the Higgs field explored a few chapters from now, suggest a genuine possibility that the vacuum we currently live inside might actually be a false vacuum rather than the true one. Our universe, in other words, might be resting comfortably inside that shallow valley, unaware that a deeper, more stable canyon exists somewhere nearby, in the underlying mathematics describing reality. Physicists first developed this general framework while studying a completely different problem decades ago, describing how certain materials can settle into locally stable arrangements of atoms that are not their most efficient possible configuration, similar to how a diamond represents a less stable arrangement of carbon atoms than ordinary graphite, despite diamonds lasting essentially forever under normal conditions on Earth's surface. That comparison offers a genuinely useful way to think about our own universe. Diamonds do not spontaneously turn into graphite during a human lifetime, even though graphite technically represents the more stable arrangement, because the barrier separating the two states remains far too high for ordinary conditions to overcome. Our vacuum may sit in a similarly durable, if not perfectly ideal, configuration. This idea might sound purely theoretical, yet it connects directly to real, measured properties of fundamental particles, values physicists have pinned down with extraordinary precision using powerful particle accelerators. Small shifts in those measured values can tip the calculation from a stable universe toward a falsely stable one, or the reverse, making this one of the most carefully watched numbers in all of modern physics. A false vacuum stays stable under normal circumstances, similar to how a hiker resting comfortably in that shallow valley could stay there indefinitely without ever noticing the deeper canyon exists. Quantum mechanics, however, never guarantees permanent stability for anything, and a false vacuum always carries some tiny probability of shifting toward the true lower state through an unusual process that has nothing to do with an actual hiker walking anywhere at all. That process involves a phenomenon called quantum tunneling, where a system can occasionally leap past a barrier it should never classically be able to cross, similar to a coin resting inside a cup somehow appearing outside the cup without ever passing over the rim. If our universe truly sits inside a false vacuum, that tunneling event carries consequences far larger than any single hiker stumbling into a hidden canyon. Consequences that could theoretically reshape the fundamental laws of physics across the entire observable universe, starting from a single, microscopic point. Somewhere, at some random location inside the observable universe, a tiny bubble smaller than a single proton could, in theory, spontaneously form, tunneling from the false vacuum we currently live inside into the deeper, more stable true vacuum described a moment ago. Physicists call this event vacuum decay, and it counts among the strangest and most extreme predictions to ever emerge from quantum field theory. Physicists first began taking this idea seriously during the 1970s, when researchers including Sidney Coleman worked out the detailed mathematics describing exactly how a bubble like this would nucleate and grow, treating the process with the same rigorous mathematical tools used throughout the rest of quantum field theory, rather than dismissing it as idle speculation. Coleman's calculations transformed vacuum decay from a passing thought experiment into a precise, quantitative prediction, one that modern physicists can test directly against measured particle properties. His work remains the foundation nearly every modern calculation on this subject still relies upon today. Inside that microscopic bubble, the fundamental fields filling space would settle into their new, lower energy configuration, and the basic rules governing reality inside that bubble would shift into something entirely different from the physics operating everywhere else. The constants that hold atoms together, the mass carried by fundamental particles, and even the basic strength of the forces shaping matter could all take on completely different values inside this bubble. Chemistry as we understand it, and quite possibly matter itself in any familiar form, could not survive inside a bubble governed by these new physical rules. Picture a single crystal of ice forming inside a glass of water that has been cooled below its freezing point without actually freezing yet. A state chemists call supercooled water. The water sits in an unstable but temporarily stable state, and a single tiny disturbance, even something as small as a speck of dust landing on the surface, can trigger the entire glass to freeze solid within seconds, the ice spreading outward from that first tiny point. Vacuum decay would work in a similar way, except instead of freezing solid, the bubble would represent a fundamental shift in the laws of physics themselves, spreading outward from that first microscopic point of origin into the surrounding space. Scientists calculate that this kind of event, while mathematically possible according to our current understanding of particle physics, remains extraordinarily unlikely to happen within any timescale relevant to human civilization, a detail explored more carefully in a few chapters. The mathematics behind this prediction rests on real, measured properties of particles like the Higgs boson and the top quark, not pure speculation invented for dramatic effect. What makes this idea especially unsettling has less to do with the odds involved, and more to do with the nature of the event itself. Current physics offers no way to detect a vacuum decay bubble before it happens, and the process would give anyone, anywhere, no advance warning that anything was about to change. Once that bubble forms, physics offers an even more disturbing detail about exactly how fast and how completely it would spread outward from wherever it first appeared, a detail that turns this theoretical curiosity into one of the most dramatic predictions in the entire history of physics. Once a bubble of true vacuum forms somewhere inside the universe, it does not sit still. The boundary separating the new, lower energy state inside the bubble from the old, higher energy state outside it begins expanding outward almost immediately, accelerating rapidly toward the fastest speed anything in the universe can ever travel. Physicists calculate that this expanding wall would eventually reach a speed extremely close to the speed of light itself, roughly 186,000 miles every single second. At that speed, nothing inside the path of the expanding bubble could ever receive any kind of advanced signal, since no warning, no light, and no information of any kind travels faster than the wall itself. This detail carries a genuinely disturbing consequence. If a bubble of true vacuum happened to form somewhere in our own galaxy, even relatively close by on a cosmic scale, nobody on Earth would ever see it coming. The bubble wall would arrive at exactly the same moment as, or even before, any light that might have revealed its existence in advance, since both would be racing toward Earth at nearly identical speeds. Picture standing on a beach, watching an enormous silent wave racing toward shore at exactly the same speed as the light bouncing off it and reaching your eyes. By the time you could ever see that wave clearly enough to react, it would already be crashing directly on top of you, leaving no meaningful gap between spotting the danger and experiencing it directly. Everything the expanding bubble touches would instantly convert into the new vacuum state, transforming the fundamental rules of physics for every atom, every particle, and every structure caught inside its path. Stars, planets, and any form of matter as familiar to us as atoms and molecules would stop functioning in any way recognizable to modern science, converted instantly into whatever new configuration the true vacuum demands. This process would not slow down, weaken, or lose momentum as it spread. The bubble wall would keep expanding outward in every direction, at nearly the speed of the light indefinitely, consuming everything in its path across the entire observable universe, unless something currently unknown to physics somehow managed to stop it. Physicists describe the speed of this expansion using a value extremely close to what scientists call the speed of light in a vacuum, the same ultimate speed limit that governs every signal, every particle, and every possible form of communication anywhere in the universe. Nothing capable of carrying a warning could ever outrun a boundary already travelling this close to that absolute limit. This detail also means the danger, however remote, would never announce itself gradually. There would be no dimming of stars, no strange readings on any instrument, and no early tremor of any kind, only the sudden, complete, and instantaneous arrival of an entirely different universe. Some theoretical physicists have explored whether extremely advanced civilizations, far beyond anything humanity could build today, might one day detect subtle, gravitational hints of a forming bubble in its earliest instance, though current physics offers no serious method for achieving even that limited form of warning. Given a scenario this catastrophic, one obvious question becomes almost impossible to avoid. Exactly how likely is an event like this to actually happen, and could it, in principle, start anywhere at all, with absolutely no advance signal of any kind? Vacuum decay does not follow a predictable schedule, a specific location, or any pattern astronomers could track in advance. The tunneling event responsible for creating a bubble of true vacuum happens purely at random, governed entirely by the same fundamental quantum uncertainty explored throughout this entire journey, the same uncertainty responsible for virtual particles, zero-point energy, and every other strange phenomenon covered so far. This randomness means the event could, in principle, occur inside a distant, empty patch of intergalactic space, deep inside the core of a star, or even somewhere inside the room around you right now, completely independent of any local conditions or events happening nearby. Quantum tunneling requires no trigger, no special circumstance, and no build-up of energy beyond what already exists inside the vacuum itself. Physicists calculate the odds of this event using something called a decay rate, a number describing the probability that a bubble forms somewhere within a given volume of space during a given stretch of time. Based on our current best measurements of particle physics, this probability comes out staggeringly, almost incomprehensibly small, far smaller than the odds of any lottery, any natural disaster, or any random event a person might reasonably worry about during an ordinary lifetime. current calculations suggest the expected waiting time before an event like this would naturally occur stretches vastly longer than the current age of the universe, multiplied many times over. Some researchers describe the odds as comparable to a specific grain of sand, hidden somewhere among every grain of sand on every beach across the entire planet, being struck by lightning during one single afternoon. Picture searching every beach on Earth for one particular grain of sand, then trying to predict the exact moment lightning strikes that one grain directly. Multiply the sheer size of that search by numbers physicists rarely need in any other branch of science, and you begin approaching the real scale of unlikelihood involved here. Physicists sometimes compare this calculation to estimating how often a specific radioactive atom might decay, except stretched across a probability so much smaller that ordinary radioactive decay looks almost instantaneous by comparison. Radioactive atoms decay on timescales ranging from fractions of a second to billions of years, and even the longest of those timescales looks brief next to the timescale calculated for vacuum decay. This comparison helps explain why physicists treat the theoretical possibility of vacuum decay seriously in their equations while feeling completely comfortable going about ordinary daily life, confident that the odds involved place this event so far outside any realistic time frame that worrying about it offers no practical value whatsoever. This tiny probability offers genuine reassurance rather than reason for alarm, since even across the entire lifespan of the observable universe so far, an event with these odds has almost certainly never happened even once. Scientists continue to treat vacuum decay as a serious theoretical prediction worth studying carefully, not because it represents any realistic near-term danger, but because it reveals deep truths about the underlying structure of the vacuum itself. That underlying structure depends heavily on the exact properties of one particular particle, a particle discovered only recently, whose measured mass carries far more weight than its tiny size would ever suggest. Every particle that carries mass owes that mass to a single, universe-spanning field called the Higgs field, named after physicist Peter Higgs, who first predicted its existence back in the 1960s, decades before anyone could confirm it experimentally. Before this field was confirmed, physicists sometimes called it simply the missing piece needed to explain why particles carry mass at all, since earlier versions of the Standard Model predicted a universe where every fundamental particle would have raced through space at the speed of light, unable to combine into atoms, stars, or anything resembling ordinary matter. The Higgs field solved that problem by giving particles something to push against as they moved, similar to how a person wading through waist-deep water experiences far more resistance than someone walking across dry, open ground, slowing certain particles down enough to give them the property physicists call mass. Confirming this field required building one of the largest, most expensive scientific instruments in human history, an underground ring stretching many miles in circumference, cooled to temperatures colder than deep space itself, in order to accelerate particles close enough to the speed of light to recreate conditions last common a fraction of a second after the Big Bang. Unlike most quantum fields, which sit at a value of 0 throughout empty space, the Higgs field carries a non-zero value everywhere in the universe, even in the emptiest possible vacuum. Particles moving through space constantly interact with this ever-present field, and that interaction is exactly what gives particles their mass in the first place, similar to how a swimmer moving through water experiences resistance that a person walking through open air never would. Scientists confirmed the existence of this field directly by detecting its associated particle, called the Higgs boson, using the Large Hadron Collider. That discovery, announced after decades of searching, completed the last missing piece of the Standard Model of particle physics, and earned its discoverers a Nobel Prize shortly afterward. Here is where this connects directly to vacuum stability. The exact mass of the Higgs boson, combined with the exact mass of a separate particle called the top quark, together determine the precise shape of the energy landscape described a few chapters ago. The landscape containing that shallow valley, representing our current vacuum, and the deeper canyon representing a hypothetical, more stable vacuum elsewhere. Physicists have measured both of these masses with remarkable precision using data collected at the Large Hadron Collider. Plugging those measured values into the underlying equations produces a genuinely striking result. Our current vacuum sits shockingly close to the exact boundary, separating a fully stable universe from an unstable one. Closer to that boundary than almost any physicist expected before the measurement was actually made. Picture a coin balanced almost perfectly on its edge, tilted so slightly toward one side that an outside observer could not immediately tell which way it might eventually fall. Our universe's vacuum sits in a strikingly similar position, mathematically speaking, based on the best particle measurements currently available. This finding does not mean physicists expect our vacuum to collapse anytime soon, given the staggeringly tiny probability explored in the previous chapter. It does reveal that the fate of the entire universe traces back, in a very real mathematical sense, to the precise mass of two subatomic particles, values measured inside a machine built underground near the border of France and Switzerland. Every time the Large Hadron Collider completes another run, smashing particles together at enormous energies and recording the debris, physicists sharpen their measurements of the Higgs boson and the top quark just a little further, refining the picture of our universe's long-term stability piece by piece. Current best measurements place our universe firmly inside what physicists call a metastable state, a technical term describing exactly the shallow valley picture explored earlier. A vacuum stable enough to last an extraordinarily long time, yet not sitting at the true, deepest possible energy available within the underlying mathematics. This conclusion carries an important caveat that keeps the entire picture from feeling like a countdown toward disaster. Even under the metastable scenario supported by current data, the expected timescale before any spontaneous vacuum decay event would naturally occur stretches so far beyond the current age of the universe that the difference becomes almost meaningless for any practical purpose. Some physicists have proposed that new particles or forces, not yet discovered by any experiment, might stabilize the vacuum completely, pushing our current state into the genuinely deepest, safest configuration available rather than a merely long-lived one. Others suspect the measurements themselves might shift slightly as more precise data comes in, potentially tipping the calculation firmly toward full stability instead. Picture a team of surveyors carefully remeasuring the exact tilt of a slightly leaning tower, using increasingly precise instruments with each new attempt. Early rough measurements might suggest the tower could eventually topple, while more refined measurements taken years later might reveal the lean sites well within a perfectly safe range after all. Physicists studying vacuum stability find themselves in a remarkably similar position, refining their instruments and their calculations year after year. Researchers at facilities beyond the Large Hadron Collider continue searching for additional clues, including experiments studying rare particle decays and searches for entirely new particles that current theories have not yet predicted. Any of these discoveries could shift the calculation significantly in either direction, reshaping this picture of our universe's fate as the data keeps arriving. Beyond the Large Hadron Collider, proposed future colliders, some stretching many miles longer than any machine built so far, could sharpen these measurements even further, potentially settling the question with enough precision to know conclusively which side of that razor-thin boundary our universe truly occupies. Until such a machine gets built and begins collecting data, physicists will keep treating the current metastable picture as our best available answer, a conclusion built from real measurements rather than guesswork, even while acknowledging that a single, more precise experiment could shift the picture meaningfully in either direction. For now, the scientific consensus treats our vacuum as probably metastable, resting in that shallow valley rather than the deepest possible canyon, while emphasizing repeatedly that this conclusion carries zero practical urgency for anyone living today, or for countless generations stretching almost unimaginably far into the future. This entire investigation into vacuum decay reveals something remarkable about how thoroughly modern physics has connected the smallest measurable particles to the largest possible questions about the universe's ultimate fate, a connection that continues showing up in stranger corners of scientific research, including one final, glowing mystery involving nothing more exotic than a simple bubble collapsing inside a jar of liquid. Fill a small glass container with liquid, then blast it with precisely tuned sound waves, powerful enough to create a single tiny bubble inside the fluid. Watch closely, and that bubble will begin flashing with brief pulses of light, over and over, perfectly timed to the rhythm of the sound waves driving it. Scientists call this strange phenomenon sonoluminescence, and researchers first documented it clearly back in the 1930s, though decades passed before anyone understood what was actually happening inside that tiny, glowing bubble. Each flash lasts an almost impossibly short amount of time, far shorter than the blink of an eye. Yet the temperature inside the bubble during that instant can rival the surface of a star. Researchers studying sonoluminescence have measured temperatures inside the collapsing bubble, reaching several tens of thousands of degrees, and some experiments have hinted at temperatures climbing even higher, rivaling conditions found inside the outer layers of stars, all generated from nothing more than sound waves, pulsing through an ordinary glass of liquid sitting on a laboratory bench. This extreme, localized heating happens without any chemical reaction, and without any external flame or spark, relying entirely on the physical compression of gas trapped inside a bubble, smaller than the width of a human hair, a genuinely strange demonstration of how much energy ordinary sound waves can concentrate into an impossibly tiny space. The most widely accepted explanation involves the bubble collapsing so rapidly and so violently under the pressure of the sound waves that the gas trapped inside heats up dramatically through simple compression, similar to how a bicycle pump grows noticeably warm as air gets rapidly squeezed inside its cylinder. That extreme heat causes the compressed gas to glow brightly for a fleeting instant before the bubble expands again and the cycle repeats. A smaller group of researchers proposed a far more exotic possibility during the 1990s, suggesting the collapsing bubble might be tapping directly into the same restless vacuum energy explored throughout this entire journey, converting a tiny sliver of that hidden energy into visible light through a process related to the Casimir effect covered earlier. Under this proposal, the rapidly moving bubble wall would act somewhat like the shifting mirrors used in experiments studying what physicists call the dynamical Casimir effect, a related phenomenon where a rapidly vibrating mirror can convert virtual particles into real, detectable photons. Most physicists studying sonoluminescence today favour the simpler heat-based explanation, since it accounts for the measured properties of the light reasonably well without requiring any exotic new physics. The vacuum energy explanation remains a minority position, tested and largely set aside by most researchers, yet it highlights just how deeply quantum vacuum ideas have worked their way into completely unexpected corners of experimental physics. The dynamical Casimir effect itself, meanwhile, has been confirmed directly in careful laboratory experiments using rapidly oscillating superconducting circuits, proving that virtual particles really can, under the right extreme conditions, convert into real, measurable photons streaming outward from otherwise empty space. That successful conversion, turning invisible vacuum fluctuations into real, usable light, naturally raises a tempting question for engineers and inventors everywhere. If empty space genuinely carries usable energy, could humans ever learn to harvest it directly? For decades, inventors and hopeful entrepreneurs have proposed devices claiming to draw unlimited free energy directly from the quantum vacuum, promising machines that could power homes, vehicles, and entire cities without ever needing fuel, batteries, or any other conventional energy source. Every one of these claims, when tested carefully under controlled scientific conditions, has failed completely. None have produced usable energy beyond what was originally put into building and running the device itself, and several were later revealed as outright fraud, designed to attract investment money rather than deliver any working technology. The reason traces directly back to one of the deepest laws in all of physics. The vacuum represents the lowest possible energy state available to any quantum field, the calmest, most settled configuration those fields can ever reach. Extracting usable energy from any system always requires moving that system from a higher energy state down toward a lower one, similar to how a water wheel only generates power because water flows downhill from a higher point toward a lower one. Since the vacuum already sits at the bottom of that energy landscape, no lower state exists anywhere in nature to extract additional energy from. A hard boundary no clever engineering has ever managed to slip past. Attempting to pull energy out of the vacuum directly would violate the fundamental law of energy conservation, a law confirmed through more than a century of rigorous repeated experimentation across every branch of physics. The Casimir effect explored earlier might seem to suggest an exception, since it demonstrates real, measurable force emerging from seemingly empty space. Engineers who examine the physics closely quickly realize this force cannot be converted into a continuously renewable source of energy, since moving the plates together using that force releases only a small, one-time amount of energy, rather than an endless repeating supply. Picture squeezing a spring until it clicks into a locked compressed position, releasing a small burst of stored energy in the process. Once locked, that same spring cannot click again and release more energy without someone first spending additional energy to reset it back into its original, stretched position. The Casimir effect works the same way, a one-time release rather than an infinite self-sustaining fountain. Patent offices in several countries have grown so accustomed to these claims that many now automatically reject any application describing a device that violates the law of energy conservation, regardless of how convincing the accompanying paperwork might appear, treating such proposals with the same skepticism reserved for claims of a perpetual motion machine. Legitimate research building on these ideas focuses on far more modest practical goals instead, particularly in the growing field of nanotechnology, where engineers study how Casimir forces affect the behavior of extremely small mechanical devices, learning to work with these forces rather than chasing the impossible dream of harvesting unlimited free power from nothingness itself. Researchers studying the Casimir effect, Hawking radiation, and the broader behavior of quantum fields keep pushing these ideas forward, not chasing free power, but chasing a deeper, more complete understanding of the strange, restless emptiness filling the entire universe. That clear distinction between genuine scientific discovery and impossible fantasy separates real physics from empty promises every single time without exception. Return for a moment to the glass box from the very beginning of this journey, sealed shut, with every trace of air pumped carefully out. At the start, that box looked like the emptiest possible place anyone could imagine, a small pocket of pure nothingness sitting quietly on a laboratory table. Everything explored since then has revealed just how wrong that first impression truly was. Inside that box, and inside every other seemingly empty space across the entire universe, restless quantum fields keep humming constantly, producing virtual particles that flicker in and out of existence trillions of times every second, exactly as they do everywhere else in the cosmos. That same restless energy pulls two metal plates together using nothing visible at all, confirmed directly through careful laboratory experiments performed again and again over the past several decades. It leaks particles away from the crushing gravity surrounding black holes, slowly converting even the most powerful objects in the universe into pure escaping radiation over spans of time larger than ordinary numbers can comfortably describe. That same energy sits at the center of one of the largest unsolved mismatches in the history of science, a gap between prediction and observation so enormous that physicists still search for its true explanation today. It may represent the very same dark energy currently pushing every distant galaxy away from every other galaxy, accelerating the expansion of the entire universe a little further with every passing year. Zoom down far enough, past every atom and every particle ever detected, and that same underlying structure churns into a foamy, unpredictable chaos at the smallest scale physics can describe, hinting at some deeper layer of reality still waiting to be fully understood. Zoom back out, and that same vacuum may or may not sit at its truest, most stable configuration, a question tied directly to the measured mass of a single subatomic particle, discovered only within the past couple of decades. Every idea explored throughout this entire journey points toward the exact same conclusion, arriving from dozens of completely independent directions. Nothing in this universe, anywhere, at any scale, in any location, from the inside of your own body to the emptiest void stretching between distant galaxy clusters, ever manages to escape this restless, humming, endlessly active foundation running beneath absolutely everything that exists. Every single idea traced through this journey started from the exact same starting point, a simple question about what fills the space between things, that question led through virtual particles blinking in and out of existence, through metal plates pulled together by nothing visible, through black holes slowly leaking away into radiation, through a mismatch in the math so enormous it earned the nickname of the worst prediction in scientific history, and finally through a bubble that could, in theory, rewrite the laws of physics themselves without a moment's warning. Space has been the main event this entire time, buzzing, flickering, and pushing against the edges of reality in ways scientists have only begun to understand. The next time someone tells you a room, a jar, or the vast reaches of outer space sits completely empty, you will know the real answer. Nothing, anywhere in this entire universe has ever truly been empty at all.